Assalamualaikum and hi everyone. My name is Nur Shazwani Akila binti Amran. My matrix number 01DDT23F1096. In this video, me and my team will present about problem-based tasks for DFN 40232 fiber optic communication system. Task 1. Understanding light propagation in fiber optic. Question 1. How fiber optic work in telecommunication system? Fiber optic carry information using light instead of electricity. A transmitter turns data like voice or internet signal into light, and the light travels through a thin glass or plastic fiber. It stays inside the fiber by bouncing off the walls. This is called total internal reflection. At the end, a receiver changes the light back into usable data. Fiber optic are fast, reliable, and good for long distance. Question 2. Optical properties of light and the impact on the fiber optic transmission. Refraction. Light bend when it enters a different material like air to glass. This helps control light inside the fiber. Reflection. Light bounces off surfaces. In fiber, it's reflect inside the core to keep traveling. For diffraction, light spread out when it hits an edge or opening. Too much diffraction can cause blurry signal. And last, interference. When two light waves mix, they can get stronger or cancel out. This can affect signal quality if not controlled. Question 3. Terms and significance in fiber optic communication. Index of refraction show how much light slow down in a material. Affects how light bends and reflection. Second, Snell's law, a rule that tells us how much light bends when it enters a new material. And critical angle, the smallest angle where light still reflects inside the fiber. If the light hit the wall at this angle or more, it stays inside. For total internal reflection (TIR), when light hits the wall of the fiber at a certain angle, it reflects back inside instead of escaping. This keeps the signal stronger. For numerical aperture, NA shows how much light the fiber can collect. A higher NA means the fiber can accept light from a wide angle. And last, acceptance angle, the largest angle from which light can enter the fiber and still travel inside it successfully.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Aibakis binti Fitri. My matrix number is 01DDT23F076. So now I will be presenting task 2 problem solving using formula. Let's begin with question number 1, which is about the index of refractions. So the formula for index of refraction is N equal to C divided by V, where C is the speed of light in a vacuum. So based on the question, the speed of the light in a vacuum, which is 3.00 times 10 to the power of 8 meter per second, and V is the speed of light in the material. So based on the question, given fiber optic material is 2.00 times 10 power of 8 meter per second. So after that, we substitute the value in the formula and we calculate, and the index of refraction that we got is 1.5. So now let's move on to question 2 using Snell law. So the formula for Snell law is n1 sine theta 1 equal n2 sine theta 2. So based on the question, we are given n1 equal to 1.00 air, n2 equal to 1.50 the fiber, and theta 1 equal to 55 degree, the incident angle. So to find the angle inside the fiber, we need to solve for theta 2. So we use the formula sin theta 2 equal n1 sin theta 1 divided by n2. Substitute the value sin theta 2 equal 1.00 times sin 35 degree divided by 1.50. That gives 0.574 divided by 1.50 equal 0.383. Now, take the inverse sign of the value. Theta 2 equals sine inverse of 0.383, which is 22.5 degree. Question 3 is about the critical angle, which tells us the smallest angle that causes total internal reflection. The formula is sin theta c equal n2 divided by n1. So, based on the question, n1 equal to 1.48, the core, and n2 equal to n.45, the cladding. So, we just substitute the value into the formula. After that, the critical that we got is about 78.5 degree. Finally, question number 4. In question number 4, we will find the numerical aperture and the exception angle. So, first we will search for numerical apertures, which is NA. So, for the formula for NA is NA equal to the square root of N1 square minus N2 square. So, given in the question, N1 equal to 1.48 and N2 equal to 1.45. Now, we substitute the value into a formula. To that, we got the numerical aperture in about 0.2965. After that, next, we need to find the exception angle. So now, this is the exception angle formula. Theta A equal to sin minus 1 in bracket NA. So we just substitute the NA value into the bracket. To that, we will got the answer 17.3 degrees. Thank you. That's all from me.
Assalamualaikum warahmatullahi wabarakatuh. And good day. My name is Norinisa Safia binti Sabri and my metric number is 01DDT23F1159. I will be explaining in task 3, which is fiber optic sketching and network design. First, for light propagation modes and index profiles. Alright, let's dive into our first type of fiber optic cable, the single mode step index fiber. As the name suggests, and as you can see in the diagram, in this type of fiber, light travels along a single direct path down the core. This is because the core of a single mode fiber is significantly smaller, typically around just 9 micrometers in diameters, similar to the multimode step index fiber, but the step index refers to the sharp change in refractive index between the core and the cladding. However, with such a narrow core, only a single mode of or path of light can effectively propagate. Because there's only one direct path, we would virtually eliminate the issue of model dispersion that we saw with multimode fiber. This allows single mode fiber to achieve very high bandwidth, making it ideal for long distance and high data rate applications. So, the trade-off for the superior performance is that working with such small core diameters requires more precise and generally more expensive transceivers and splicing techniques. So the keyword is single mode, only one path for light. Alright, next let's continue our second propagation modes, the multi-mode step index fiber. As you can see in the diagram, light rays from the source take multiple paths as they travel down the fiber. This multi-mode characteristic arises because the core of this fiber is relatively large, typically around 50 or 62.5 micrometers in diameter. Notice how the light rays are bouncing off the cladding at various angles. Well, this is because the step index profile, meaning there's a sharp step like change in the refractive index between the core and the cladding. Because light takes these different, longer paths, some rays arrive at the other end slightly later than others. So the phenomenon is called model dispersion, and it ultimately limits the bandwidth or the amount of data this type of fiber can carry. So, on the plus side, the larger core size makes it easier to work with and allows for the use of less expensive transceivers and splicing techniques. While it has lower bandwidth compared to other fiber types, its cost effectiveness makes it suitable for certain shorter distance applications. So remember, the key point is multi-mode for multiple paths for lights. Now, let's explore another type of multimode fiber, the multimode graded index fiber. Like the multimode step index fiber we discussed earlier, this type also has a large core, typically around 50 or 62.5 micrometers. Right, it's just the same as the other one that we discussed just now, and allow for multiple paths of light to travel. However, the key difference lies in its graded index profile. Instead of sharp, step like change in refractive index at the core cladding boundary, the graded index fiber has a refractive index that gradually decreases as you move from the center of the core towards the cladding. Do you notice in the diagram how the light rays follow the curve paths? This continuous refraction towards the center occurs because light travels slower, the denser, higher refractive index at the core's center and faster in the less dense, lower refractive index towards the edges. This ingenious design helps to equalize the travel times of different modes. The rays taking longer paths now towards the edges actually travel faster through the lower refractive index, and it allowed them to catch up with the rays traveling straight down the center. So as a result, multimode graded index fiber offers a medium to high bandwidth, significantly better than the multimode step index fiber. While it generally requires moderately more expensive transceivers and splicing compared to the step index multimode, the improved bandwidth makes it a valuable option for intermediate distance applications requiring higher data rates. So, the key point is for the multi-mode, multiple paths for light is similar just the second one, but this one is ingraded index, which is refractive index gradually decreases from the center, and it has a curved light paths. Visually trace this in the diagram, just like the diagram above. All right, moving on from the types of light propagation within the fiber, let's now shift our focus to the physical cables themselves and explore the differences between indoor and outdoor fiber optic cables. As you can see in the illustration, these cables are designed with different environments and requirements in mind, leading to variations in their construction and protective layers. Now let's take a closer look. at indoor fiber optic cables. As the name suggests, these cables are specifically designed for use within controlled indoor environments. You can see in the diagram a typical layer construction. Indoor cables are engineered to withstand the normal temperature and humidity fluctuations you would find inside a building. They offer resistance to moisture and common indoor chemicals. A key focus in their design is flexibility and a smaller overall size, making them easier to handle and route around corners and within tight spaces inside buildings. Generally, indoor cables are less expensive compared to their outdoor counterparts. Their primary applications include connections within buildings, such as linking network equipment, creating path cords, and connecting devices within a data center or office. Finally, we have outdoor fiber cables. As you can see from this detailed cross section, these cables are built for a much tougher life, designed to withstand direct exposure to the elements. They are engineered to handle wide temperature swings from extreme heat to cold, and crucially to prevent water or moisture from penetrating and damaging the delicate optical fibers within. Outdoor cables also offer resistance to a broader range of environmental hazards, including chemicals, oils, and pollutants. Their construction often incorporates strengthening elements and robust outer jackets to withstand physical stress, including tension, crushing forces, and impacts that might occur during installation or due to environmental factors. Due to their rugged design and the challenges of outdoor environments, these cables typically require more careful and often more complex installation procedures, and they are generally more expensive than indoor cables because their primary applications lie in outside plant networks, directly burial, and aerial installations, forming the backbone of our wider communication infrastructures. Okay, that brings us to the end of my part on fiber optic sketching and network design. We've covered the basics of light propagation modes, index profiles, and the differences between indoor and outdoor cables. I hope my explanation is clear. Thank you for watching.
Hi, my name is Rachel Kashmira, anak perempuan Sindil Kumar. My matrix number is 01DDT23F1134. Today I will explain wavelength division multiplexing, or it's called WDM. WDM is the technology used in fiber optic communication. It allows us to send many signals through one fiber optic cable at the same time. Each signal is sent using a different wavelength or color of light. This is useful because it increases the amount of data we can send without needing more cables. It's like a highway where each car travels in its own lane. Each wavelength carries a different data streams and they all move together through the same fiber. There are two types of WDM. One is CWDM, which is coarse WDM, used for shorter distances. Second is DWDM, dense WDM, used for long distance and faster data. WDM makes internet connection faster and more efficient. Now I will explain fiber in the loop, also called FITL. FITL is a type of fiber optic network that brings fiber closer to our homes or buildings. It replaces the old copper lines and improves internet speed and reliability. There are different types of FITL. The first one is FTTH, fiber to the home. which is fiber goes directly into your house. Second is FTTB, fiber to the building. Fiber reaches the building, then copper is used inside. The third one is FTTC, fiber to the curb, which means fiber goes near your house, then copper completes the connection. The fourth one is FTTP, fiber to the premises, which means a general term for FTTH and FTTB. FITL is important for high-speed internet, especially for streaming, video calls, and smart devices.
Task 6. Passive Optical Network PON Implementation. First, sketch and label the structure of a PON from ISP to the end customer. At the top of the diagram, we have ISP. This is the starting point at the service provider's central office. It sends and receives optical signal to or from user. And then we have a fiber that connect between splitter and ISP, the medium used to transmit light signal from the ISP towards the end user. It's passive, meaning it doesn't require power. And for the splitter, a passive optical splitter divides one incoming optical signal from the ISP into multiple outputs. This enables the sharing of one fiber link among multiple customers. And for the last, we have the end customer. We have ONT or ONU, which is Optical Network Terminal or Optical Network Unit. These are located at the customer's end, like home or businesses. They can convert optical signal back to electrical signal for the user's device. And we have home too, which is the business. Both have ONT or ONU unit. And then one output is specifically labeled as BIP1 ONU, indicating it supports broadband PON. For the question 2, main components of a PON. Optical line terminal OLT, located at the service provider's end, send data downstream to user and receive upstream data. Manage bandwidth allocation and control the network. For the optical network unit ONU, convert optical signal from fiber to electrical signal, usually installed in building or nearby cabinets. Optical network terminal ONT, similar to ONU but installed at the customer premises like home, and provide internet, TV and phone service. And last, for the splitter, a passive device that split the fiber signal from the OLT into multiple outputs. No power supply needed, can serve 32 or more customers from one line. For the last question, we have type of passive optical network. First, APON, and the speed is average 155 Mbps. The efficiency is older and ATM based. We can apply in early broadband network. For BPON, up to 622 Mbps and more efficient than APON. We can apply in voice, video, or internet. And for GPON, up to 2.5 Gbps, and it is very efficient and flexible. Widely used today for FTTH, fiber to the home. And last, we have EPON, up to 1 Gbps. It uses Ethernet, easy to integrate with LANs, and usually used in businesses and residential use. That's all from us. Thank you.